I'm Tim Ventura from AmericanAntiGravity.com, and I'm speaking this evening with Sam Barros, the designer of PowerLabs.com and a double major electrical engineer, mechanical engineer, who works with several advanced technologies based on electromotive force. This includes railguns, coil guns, Thompson gun, a variety of different technologies, not all of them weapons, but definitely interesting. Sam, can you hear me okay?
Yeah, perfectly. Well, there's powerlabs.org and there's power-labs.com. I have two domain names.
Well, I guess I should get started by asking you, just in general, what draws you to these kinds of technologies?
Well, I guess ever since I started experimenting with electricity, I've been fascinated by the behavior of electricity at very high power levels, the kinds of magnetic fields you can get, and the effects those fields can have on different things. One of the first things I ever did when I got a capacitor was to short circuit it, and I was amazed by how much power you can get from even small energy levels in a capacitor. So ever since I found out about that, and I think I was about 9 years old at the time, my research has been a quest to essentially find out how much power I can deliver and how I can harness this power to do useful work with it, be it form a piece of metal as in my can crusher, or levitate a metal ring with a Thompson's coil, or accelerate a projectile with a railgun.
Well, I should be upfront and say that your website is incredibly well done. It's one of the few that I'm very envious about in terms of just the way it's put together and the look and feel, and then the content. You know, you really can't beat the kinds of experiments you're working with. With anti-gravity technologies and the research into it, you know, every now and then something tends to work, but a lot of it is theory and ideas still. And with your website, it's just project after project after project with incredible results and photos and footage. So, congratulations on putting that resource together, because myself and thousands of other people appreciate your work.
Well, thank you, Tim. I think the main reason why I put the page up in the first place, why I spent all the time in coming up with the pictures and making the video and typing up the content, is because I know that there are a lot of people like me and like yourself that are interested in these things, and we feel frustrated that we have this quest for knowledge to find out more about things that are not taught in everyday school, and there are no sources for them. You know, if you go into a library, you're not going to be able to find any information whatsoever on the can crusher, for example. But this is something that's really interesting. It's something that people want to know more about. So that's why I went out and I made the webpage. I am doing it because it's the kind of thing I'm interested in, and it's the kind of thing I would like to see online.
Definitely. Well, for those people out there who might not be familiar with it, the can crusher, and please correct me if I'm wrong, uses a few turns of wire connected to essentially a capacitor bank and a spark gap, and when it fires, the wire constricts from the magnetic force and squeezes the can down. Now, you've
Well,
also...
actually, it's a little bit more interesting than that. What actually happens, and your description is right, it is a capacitor bank being discharged into a coil of wire. But what actually happens is that when the current flows through the coil of wire, it creates a magnetic field. And the magnetic field induces an eddy current on the can, that is a rotating current around the metal body of the can. And the current on the can has its own magnetic field. So as the magnetic field of the can repels the magnetic field of the wire, the can is crushed inwards by a magnetic force. There's no contact between the can and the wire. In fact, you can even wrap the wire around a PVC pipe, and it will crush cans inside the pipe without deforming the pipe.
Well, I hadn't realized that. So the can actually crushes itself then.
Yes, entirely by a magnetic force.
That's amazing. That's amazing. Now, in addition to that, that's one of many technologies. One of the ones that I've recently been experimenting with is a Thompson's gun, or a mass driver that Information Unlimited put together. And the one that they've developed, I was incredibly impressed by the output of it. But it's kind of small potatoes compared to some of the things that you've worked with, right?
Well, it is a very impressive device, and it's very interesting you should mention it after the can crusher, because a Thompson's coil and a can crusher are essentially the same device. In the Thomson's coil, you pulse a magnetic field through an aluminum ring, and that creates an eddy current on the aluminum ring, and the aluminum ring is repelled by the field. If you were to put the aluminum ring inside the coil, it would crush just like a can. In the same way, if you were to put the can right outside of the crushing coil, the can will be fired outwards instead of being crushed. It's actually the same technology.
Oh, I didn't realize that.
And that's why you see so many experiments with common themes on my webpage. For example, the coil gun and the railgun, and my own experiments with Thomson's coil and the can crusher. These are all very interesting technologies, and it may seem like really new ideas, but if you really look at it from a technical point of view, they are actually all pretty much the same thing. Once you have the basic power supply, once you have a powerful enough capacitor bank, and once you have a switch that can switch the capacitor bank energy, you can feed that power into basically the same coil and get it to do different things in different configurations. The same can crushing coil can be used as a coil gun, and if you modify the coil a little bit, you can use it as a Thomson's coil, and the railgun will use the exact same power supply, although that's a slightly different device.
Well, the device that I was testing, which Bob Iannini had sent over from Information Unlimited, I believe, I can't even tell you offhand what the energy that it used was. It was a high energy device, although one of the limitations has traditionally been energy storage. And there's been a lot of buzz lately about supercapacitors and the possibility of using aerogel or some of the newer composite materials to store more energy. Do you think that some of these newer technologies will give us higher energy densities in the near future for devices like this?
Well, I know for a fact that they will, and there are a lot of things that exist today that can give us unsurpassed energy levels. For example, if you induce a rotating current in a superconductor, you can essentially store as much energy as a superconductor will allow you before it saturates, and those energy levels are well beyond anything a battery could produce. Similarly, a superconducting inductor can be used to store very large amounts of energies. So the fact is that there are technologies out there that will allow us to, let's say, to overcome the energy storage barrier, which has so far made compact and practical electromagnetic devices. Essentially, it has made them much too large for any use aside from a laboratory. But the problem is that these technologies are much too expensive today, and I think as their price comes down, we're going to be seeing more and more use of them. Now, you mentioned the supercapacitor. My understanding is that this is a technology developed by Maxwell, and it's essentially somewhere in between an electrolytic capacitor and a battery. Now, a battery is going to store far more energy than any capacitor would because you have a chemical energy storage method. And then on a conventional capacitor, the energy storage is purely electrostatic. However much energy your capacitor will store will be determined by what kind of dielectric you're using, how much voltage it will hold back, and what the dielectric constant is. Now, the supercapacitor, my understanding is that they're using some kind of very high surface area dielectric, and it's chemically etched. So the chemical etching is, it could be linked somewhat to the idea of a battery. You're basically electrolyzing the anode plate and forming a very thin dielectric layer. And because it's so thin, you can have a very low voltage standoff, and it also has a very high dielectric constant. Now, the problem with that is, since it's a chemical process, all the power has to flow through the electrolyte. And as we all know, liquids are just not very good conductors of electricity, definitely not comparable to the metal plates you would see in a capacitor, in a conventional capacitor.
Yeah, definitely.
So the end result is you do get a lot more energy storage, but at the cost of a much higher internal resistance. So although chemical ultracapacitors will give us very compact, high-power power supplies, they won't pulse as quickly as, say, a railgun would require. They're very low-voltage devices, probably 2 to 5 volts per unit, and with their very high resistance, you would have to bank so many of them in series that the end result would be an impractical resistance. It just wouldn't be able to pulse fast enough to power a railgun.
Oh, I see what you mean. It's more like a battery than really the high discharge necessary for a lot of the devices. Now, in terms of
Exactly. It was the same dilemma as with electrolytic capacitors. Conventionally they've stored far more energy than conventional capacitors, but they also have a far higher equivalent series resistance.
well, in terms of railguns, I didn't realize this, but you were approached. Now, I believe it was the U.S. military was actually interested in some of the rail designs you'd come up with.
Yeah, well, they were interested in the United States Naval Research Laboratory was interested in hiring me, and the person I spoke with, I don't believe I'm at liberty to share his name, especially in an interview, but he was telling me that they're starting a new railgun research, and he is in charge of putting together a team to assemble this railgun over the next couple of years, and he was interested in hiring me for that.
Oh,
But unfortunately, it seems like the Department of Defense has some kind of policy against hiring non-U.S. nationals, and me being from Brazil, that unfortunately prevented me from being able to take the job.
yeah. It sounds like kind of the bureaucratic logic, but it's unfortunate because yeah, the things that you've been able to do on the website, I mean, just the kinds of velocities you're able to get and the kinds of experiments that you're doing. When you take into account that you're a lot like myself in working on a complete shoestring budget, given the resources, in fact, what do you think you might be able to achieve if you had the government style funding, that level of funding?
Well, I think what differs my research from a lot of the governmental research is that I have a very hands-on, practical approach to things. A lot of people like to theorize and put together a couple mathematical equations and try to model a device that they've never built. And modeling is a really powerful tool when it comes to building things, but for a lot of new technologies, the models just fall short because when you're trying to find out something new and you don't know for sure what you're expecting as an outcome, you basically just have to throw numbers out and say, okay, I estimate that I'm going to be seeing this much force. And in the end result, those models are very limiting because you start to believe something uh, that that's theoretical and it may or may not work in practice. So I prefer to go out and build a device to the best of my knowledge and then start experimenting. And given enough resources, my favorite kind of experimentation is to actually build it and start increasing the power level until something breaks. And then when something breaks, I strengthen that part and then continue increasing the power level from there until something else breaks. And that's actually how they build race engines. It works for racing. It works for a lot of other things.
Sure,
So
sure.
I think given more resources, I would be able to put together something a lot better than my initial railgun, which was actually built my first year of engineering school over summer. So it was very crude, very little design behind it, and basically whatever parts I could get in a very small time frame. But whether that would be better than the design they have or not, I don't know. It would be different, and I think that's the most important thing is looking at things from different perspectives. If you only look at it from one point of view, you might be missing out the greater picture. You might be missing out ideas that might be a little bit different from what conventional theory would tell you, but equally valid.
That makes a lot of sense. Almost by definition, innovation has to fall outside of the model, at least to some degree. And so, by not restricting yourself to just doing math, this is something that's affected anti-gravity research and tinkering to a large degree. And every time a new idea comes along, there's always the confrontation between the limits of the model and then what experimenters are willing to do to go above and beyond that. And it definitely seems like you're doing the same thing with electrical engineering in power electronics. One of the things that I'd wondered about it, I took EE courses in college, but ended up switching majors. And one of the things that kind of drove me out of it was I had an interest in Tesla and power electronics and many of the same things that you've worked with. But I noticed at the time everything was going towards microelectronics. And I'm wondering if you have any thoughts on that as far as how the industry is changing and, if it makes your skill set, I guess, all that much more unique.
Well, I guess this kind of brings me back to when I was interviewed by the main engineer in Junkyard Wars, the DLC show I was in. He was asking me what kind of engineering education I had, and I told him about that, and then he's like, well, that's great, but, what can you bring into the show? And I said, well, aside from my engineering education, I'm a certified machinist at the university. And he was really surprised at that because he was an engineer himself, and he said that he has never heard of a university um, giving engineering students machine shop classes because that's definitely not what you're expected to do out in the real engineering world. And he said that a person with those skills would probably be really sought after in the industry because when you don't know the machining aspect of engineering, you're not going to be able to design things that are machinable. You're going to say, okay, well, this is the best design, and then the machine is going to say, well, that's a really good design, but we can't build it.
Yeah.
So in the same way, as the electronic industry moves towards microelectronics and miniaturizing everything, and everything now is going digital, it's going to bring about great benefits in essentially everything but power electronics, because we can make really small computers and we can make really fast processors, but none of that technology is ever going to be able to switch 1 million amperes. And as a matter of fact, it will all break down when it's exposed to any kind of electrical disturbance. So as it miniaturizes, it becomes more sensitive.
Sure.
But at the same time, once you get into the master's level in electronic engineering, you can take power classes that actually deal with the kinds of devices that you would need to switch very high powers. It's really specialized education, and it's not something that I have access to yet because I'm still in the undergrad level. But it's out there. I guess there are not many engineers that deal with that kind of stuff, but there are a few, and I hope to be one of them when I graduate.
Yeah, well, you're definitely on your way. One of the things that I would be remiss if I didn't ask about is in working with the lifters and high voltage technology, I started to notice anomalous effects. And, it was difficult to describe, but it's one of those things that's almost kind of, you notice it when you work with it on a day-to-day basis. And, I should ask, with the power electronics, and, you do high voltage work and high current pulse work and lots of work with magnetics. Do you ever notice any anomalous effects with that? Anything that might kind of fall outside of, what's taught in science? Maybe just something that was overlooked in the textbooks.
Well, I see that when I really try to push the envelope, sometimes my knowledge falls short of what I expected. Sometimes things happen that I can't explain. For example, I designed a railgun to withstand 5 times the calculated magnetic repulsion force between the rails, and then I fired the gun at full force, and it actually broke the rail enclosure in 7 different places. And mathematically, there is no way that the rails could ever have produced that much force. The power supply would not be capable of feeding it enough current to force the rails apart with such a force that would break the rail enclosure. But, when I'm faced with something like that, I always try to look at, okay, so it wasn't the magnetic field. What else could have done it? And you'll find that a lot of those things are essentially a little outside of conventional theory, which is the reason why I overlooked it. But more often than not, they have very interesting explanations that follow the usual realms of science. In the case of the railgun breaking, I found out that there was an arc between the rails and the projectile, and the arc vaporized the rail material, and it just created such an enormous vapor pressure that the pressure itself forced the rails apart instead of the magnetic field. So, as you were saying, you do see a lot of unusual and very strange effects, but More often than not, I find that I can at least come up with an explanation that satisfies me, or at least come up with an explanation that, whether it is 100% right or not, is at least sufficient to guide me in the right direction as far as solving the problem or overcoming the difficulty goes.
Definitely. Well, one of the issues that I've had in terms of going beyond the conventional knowledge is, I interviewed John Hutchison a while ago, and it just comes to mind because I just processed a bunch of video for him. In fact, I think I may have sent you that clip. But he's got some of the most interesting technology out there, and the more I watch it, the more interesting it is. I've tried to come up with 100 different ways to fit it into conventional high voltage electromagnetic theory, but it just nothing seems to fit. Do you have any thoughts on the Hutchison effect at all?
I think it's fascinating. I haven't read too much about it, but I saw a video, and I would agree with you that it is well beyond, uh, well, at least a full explanation is well beyond the realms of conventional science. But having said that, one thing that occurred to me is I have a friend that does ballistic tests, and he fired a Teflon bullet out of a high-powered rifle, and the rifle itself, I think it was a 30-06, which shoots at about, I'm guessing, 3,500 feet per second, and that's with 150 grain bullets. So if you put a Teflon bullet in there, you've got about 10 times less mass. It will go a lot faster. He was saying that he could fire the projectiles at over 4,500 feet per second, and he told me that the Teflon bullet was able to fully penetrate and come out the other side of a 1-inch thick steel plate. Now, this sounds completely incredible, and incredible in the sense of hard to believe. But a lot of railguns that operate with plasma armatures, they have to shoot non-conducting projectiles, and polycarbonate is one of the most widely used projectiles for those guns because it withstands a lot of pressure without cracking. And
Sure.
those guns will punch sometimes 4 inches of steel with nothing but a solid polycarbonate block. So how is it possible that a soft plastic, which is actually deforming as it comes out of the gun because it's going so fast, can go through something as hard as 4 inches of steel? And there are a lot of explanations about that, several different theories, but I came across one that's very interesting. When you look at the velocity of the projectile, and then you look at the mean velocity of the molecules, because that's what temperature is. An absolute temperature reading is basically telling you what the mean velocity of the molecules are inside the structure, how fast they're vibrating. You will find that at very high velocities, right around 4,500 feet per second for steel, the projectile is moving about as quickly as the molecules are moving inside the material. So the theory I was discussing with this friend of mine is that perhaps once something goes as fast as the molecules in the material, it's able to make its way around them. Essentially, the material behaves as if it was molten. So then the second theory comes, what if you could vibrate a material at that frequency? What if you could vibrate it at the frequency at which the molecules would be moving as fast as if they were moving when the material was molten? And I think perhaps if you could vibrate a material like that, it would act as if it was molten, even though it was not, because its molecules are vibrating at the rate that they would vibrate if the material was molten. And I guess you could link this a little bit with ultrasound atomizing water. If you direct a beam of ultrasound at water, the water will mist up into the air, but it's not vapor, it's actually being physically broken up.
Yeah.
So although I have no idea what really is behind the Hutchison effect, I think that maybe something worth investigating would be the possibility that perhaps the materials could be vibrated at such a frequency that their molecules would just slide past one another, and the material would behave as if it was molten, and you'd be able to put different materials together because their molecules are free to move and bond with other molecules.
It definitely matches with some of Tesla's idea about mechanical resonance. I've heard several other theories. One of the latest and most intriguing being that perhaps something like a collection of magic frequencies are changing electron orbitals and allowing the chemicals to, in a sense, almost behave as other chemicals. But one of the challenges for me, just with my particular area interest, is not so much even the melting. It's more of how is he able to make things like the 70-pound bowling ball lift off, and that's that's a topic for another conversation. But it's definitely something that's a challenge. Well,
Yeah.
with
My catch with the electron orbital changes is that whenever you bring an electron up to a different orbital, it will have to come back down, and the only way it can do that is by emitting radiation. So if that was the explanation, you would expect to see a lot of light being emitted, a lot of infrared, maybe even microwaves, and that's not something I observed in the experiments.
yeah, and in his case, I'm not sure how much of that they've really tested for. I've there are a number of different theories. I think it's definitely 21st century physics. I think it's the kind of thing where maybe in 50 or 60 years we'll start to understand really what's going on with it. Although the roots of it are probably based in the here and now of science. Well, in terms of the projects that you've worked on, I've covered a few. The railguns, where you have Lorentz force accelerating a projectile, and then the Thompson gun, which is more of a Lentz law, and you can use that. There's a restaurant in Vancouver that has a wok, a Chinese wok that levitates based on that also. What are some of the other things you've built? I know that you've worked with microwaves a little bit.
Yeah, well, I worked a lot with chemistry. I had a fully equipped chemical laboratory, and I essentially challenged myself to synthesize different materials. So I was actually going to major in chemistry initially, but then I found out that most of the jobs in chemistry are in the pharmaceutical industry, and that's very boring. So I figure I'll take something more um, mechanical, I guess. So I've done a lot of work with chemistry. My first real science project was actually alternative fuels. I built a liquid air powered engine, which is essentially, I guess, a gas turbine where you store liquid air in a cryogenic tank and you run it through a heat exchanger. You bring the liquid air up to room temperature, it vaporizes, the vapor warms up, there's a lot of expansion, and this expansion pressurizes the gas because it has nowhere to go, and then you use a high-pressure gas to run a gas turbine. And that was actually how I came to the United States the first time. I was representing Europe in an international science fair in 1998. So I did a lot of work with alternative fuels. I worked a lot with microwaves, which earned me a spot on MTV as the microwave expert for the Big Urban Myth Show.
Oh, okay.
Yeah, it's pretty interesting. MTV saw some of the experiments I did, and they thought I knew a lot about microwaves, and so they invited me to be on the show. Most of my previous work was actually revolved around microwaves. I was studying the ball lightning phenomena. I'm sure you must have heard of it.
Yeah, definitely. Someone else who's done a lot of work with that is Jean-Louis Naudin in France on the JLN Lab site. What?
Yes, that's right. He also does a lot of work with lifters too, I think.
Yeah, what were you able to find with ball lightning?
Well, essentially, I don't know if the ball lightning you can create in a microwave oven is the same as the one that has been reported to exist naturally, but what I found is that essentially any time you have a conductive vapor inside a strong enough magnetic microwave field, the microwaves will excite the conductive vapor because the conductive particles will intercept the microwaves and they will heat up. And once it becomes hot enough, it will ionize, and it gives rise to a luminous plasma ball, which is essentially just ionized conductive matter absorbing microwaves. And as long as it continues to pick up microwaves, it will remain ionized. It will give off light and heat, and it will remain inside the microwave oven, basically until something breaks.
I have a file. When I was doing a lot of my research, I started doing research in '92, I think, and I started college at 16. I found a paper buried in a book written in the 1960s. Actually, I'll forward a copy of it to you. It's a kind of a formula that Tesla came up with. I guess an engineering formula that he claimed created ball lightning. And In his case, he claimed that it didn't require any of the gases or any of the carbon compounds that have been commonly used. But, on the flip side, I've never tested his theory, and the videos that have been floating around online, pardon the pun, have been really convincing. The electrified gas cloud, it really just, it has the look and feel of what you would expect ball lightning to look like.
Yeah, well, if the microwave field is strong enough, you can actually get anything to become ball lightning. For example, with very high power microwave waveguides, such as the ones used in telecommunications, the waveguides have to be evacuated because if there was any gas inside them, the very small fraction of a percentage that the air would absorb of the microwaves would be enough to heat up the air to its ionization point, and then once anything ionizes, it becomes a plasma, and then the plasma is really conductive, so it's going to pick up a lot of microwaves, and the ball lightning will become very hot, and it will grow, and it will destroy the waveguide. So just because a microwave oven has a very low power, you need a conductive compound, not necessarily carbon. I've done it with aluminum powder, magnesium powder, iron powder, but it has to be conductive. And it just needs to be conductive so you can get the initial ions out to form the initial plasma. But as the field becomes stronger, as you go higher and higher in power, you can get microwaves to ionize basically anything. I suppose with about maybe 100 to a couple 100,000 watts of microwaves, you could create ball lightning out in the open air. It would probably melt the waveguide, but it would form. Now, Tesla had a totally different approach. Nikola Tesla was talking about using a bipolar Tesla coil system, and there were two coils of different sizes, and I forget what the number was, but he said that if they resonated at different frequencies in such a way that there was a beat, in other words, every X amount of cycles, the frequencies matched up, and you gained constructive interference, and there was a power peak, he said that could bring about ball lightning. And to the best of my knowledge, someone did replicate that, and I can't remember if it worked or not, but I think a search at the Tesla list on Google would probably yield it. It's just a search for Tesla coil ball lightning, and I think it was two brothers that did the work, and they published the results on maybe IEEE transactions. I'm not sure. It was published in some kind of professional research paper, so the information's out there.
Yeah. It almost sounds like Tom Bearden's scalar overlaps that he's attributed to Tesla. The two peaks, the two waveforms peaking at a specific point. Tesla did a lot of work with that, so it's interesting to see yet another example of it. Although it sounds like this one has some validation. Well, one of the things that I should kind of finish up with, because we're running a little bit low on time, but in the 5 to 10 year range, I'm assuming you're going to keep going and learning and putting things up online as you build them. What can people expect to see on the Power Labs website?
Well, I guess my first priority is going to be to finish my current project. So I'm going to finish my current railgun, which is a square bore design. I'm using smaller rails, and it's basically it's a test of new construction techniques. I'm trying out a new material called G11, and it has a higher tensile strength than the G9 I used before. And that, together with the new construction techniques, should yield a railgun casing that's unbreakable. So once I'm convinced that works, I'm going to be working with a externally augmented railgun, which is going to use permanent magnets to create an artificial magnetic field between the rails. And then once power is applied, the rail's magnetic field adds on to the magnet's magnetic field, and you can produce more force with less current. So that's pretty much going to be the last of my railgun research, simply because I don't have the money to continue building larger and more intricate designs. I'm probably going to finish my turbine research, and I still have to finish a Marx generator that I'm building. I still have another voltage multiplier to finish. And then once that's all done, I'm probably going to start studying lifters, because that's something I've always been fascinated by. And my university has an aerospace laboratory with vacuum chambers where I could try out all sorts of different lifter tests. They have thrust stands that I could use. But I guess once that research is all done, I'll be out of college and I'll be looking for a job. And I don't think it'll be the end of Power Labs, but it might be the end of my day-to-day updated research, because once I'm out of college, I probably won't have the time to research as much.
Yeah,
And then I like to think that with time, I will make some money out of my job, and I would like to start my own company. And I think it would be a very fitting name to call my company Power Labs, and it would be an engineering consulting company where I would basically be hired by companies to do special designs. For example, let's say a dance club wants a 10-foot diameter plasma globe on the dance floor, and then they would hire me, and I would design it and have someone build it. And then I guess it would be very interesting to have that kind of work go up online as a continuation of Power Labs, but with other people's funding, because it's getting pretty expensive for me to pay for all my projects out of my own pocket.
Definitely. Well, I should wrap things up for this evening. Again, it's powerlabs.org or power-labs.com.
Yep.
Okay, well, thanks again, Sam. Have a great weekend.
Yes, Sam. It was a pleasure talking to you, and I'll look forward to talking to you again in the future.
Oh, definitely. Definitely. We'll have to keep updated on your research. Have a good one.
Same to you. Goodbye.
Bye.